Welcome to today's lecture. So in this lecture, we're going to be going over motion diagrams. Here it says 1D. We are going to really briefly look at a two-dimensional one, but we are going to be focusing on one-dimensional motion first. So primarily what we will be dealing with is one dimension, but we will do one 2D diagram later. So last time we introduced two new concepts, this thing called a scalar, which is just a number. So numbers can be positive or negative, but there's no direction associated with it. So something like you could have positive money or you can owe money being negative money, that would be a scalar. Temperature, another scalar. We also introduced this thing called a vector, which is a magnitude, which happens to be a number, and a direction. So there's some sort of direction associated with how you're going to be describing your vector quantity. And we talked about two different ways in which we can represent vectors. We had our magnitude and angle. Oops. Where we were going to have it some angle, we were representing it in degrees with respect with respect to a certain direction, so clockwise or counterclockwise from some axis, positive, negative x, positive, negative y. Or we could use our unit vector notation. So we could have some vector v, it would be vx I hat, indicating that this value of vx is pointing in the x direction, plus vy j hat, so value vy pointing in the y direction. And if we had a third dimension, the z direction, we'd have vz, so the value in the z direction, and the k hat pointing for z. So both of these are ways we can represent vectors. This time we're going to be focusing a little bit more on drawing vectors, where we saw that the symbol for a vector is going to be an arrow. So we're going to be drawing a lot of different arrows today. So what we're going to be covering, so in the first video we're going to be looking at concepts of motion as well as models and modeling. In the second video we're going to go over position, time, and displacement. And then in the third video, we're going to cover velocity and linear acceleration. So here, when we're discussing velocity and linear acceleration, we are going to actually be focusing on the average value. We will discuss other types of velocity and acceleration later. I want to say in the next 2 to 3 lectures. So let's talk about motion diagrams. But before we can really talk about motion diagrams, we need to formally define what motion is. So according to physics, motion is defined as the change of an object's position with time. So where an object is located can change with time, and that is the definition of motion. So there's a lot of different ways in which humanity acknowledges motion. We can talk about it in a couple of different terms. So for cars, for various modes of transportation, cars, boats, trains, airplanes, we a lot of the time talk about speed, right? How long or how fast we can go from point A to point B. That is talking about the motion of that particular mode of transportation. You can also talk about, rearranging your living space. You are moving all of your objects around. They're undergoing some sort of motion. Ideally, you're not literally in bed all day. You get up and do something, whether that's just go to the bathroom or walk to the fridge and grab some water and some snacks. You've gotten up and you've moved. You've changed your position. Even if you changed it back to where you originally were, there's still motion that has occurred. So the 4 types of motion we are going to be looking at in this class are going to be linear motion, which is going to be the first type of motion that we focus on, so just moving in a nice straight line. We're going to come back to circular motion about halfway through, or a little over halfway through the semester. So moving in a circular path, and we are talking about perfect circles in this case. We have projectile motion. So in this case, it's being launched and it'll come back down. This is something we're going to be discussing relatively soon. So we're going to go through our linear motion, then we're actually going to discuss projectile motion. And then we have rotational motion, where an object has some sort of axis and a point will rotate or move around that given axis. Now, these three, linear motion, circular motion, and projectile motion, we are going to be defining as translational motion in this class. And with translational motion, we're going to be making an approximation that our object doesn't rotate. So our object is going to be always pointing in the same, not always pointing in the same direction, but we're not going to care how it goes in linear motion. We're not going to care about how it goes in circular motion, and we don't care when we throw things for projectile motion, they probably have some spin to it. We're going to ignore it because it's not going to be relevant to the math we're going to be using. And so we kind of approximate a lot of this motion as translational. It just kind of slides along this particular path. So we want some way to represent how our object is moving or the object's trajectory. So trajectory is just the path in which your object is going to move. It doesn't matter if it's linear, circular, projectile, or rotational motion. Trajectory just always talks about how is your object going to be moving around. So we want some sort of way to represent this. So let's pretend we have a friend who wants you to take pictures of their car. So you're going to stand in place and they're going to drive by and they're just going to go to the right. So here they have their car and they're going to be moving to the right. So a couple seconds later, they're some distance to the right. And we're going to put our camera on a shutter and we're going to take pictures for a fixed amount every couple of seconds or milliseconds, whatever your hypothetical friend happens to want here. So we're going to make sure that it's set to an automatic shutter speed. So it just takes the same, every 2 seconds it takes a picture, for example. And what's going to happen is this is our first picture, right? Our car is all the way on the left side of our frame. The next picture, it's going to have moved some distance, in this case to the right because the car is moving to the right. And I can take another picture and it's moved to the right some more. And I can take a fourth picture and the car has continued moving to the right. So this here is a series of photos that I've taken and they're all individual. And I can see that the car is approaching the palm tree. So each one of these photos, it's kind of a series of unrelated photos as it is. So if I printed these out and accidentally dropped them, I could probably figure out what direction this car was going because I took the pictures, but if some random person had to try to put them together, they might not realize that these are a series of photos taken one right after the other. And I just think it's a bunch of different random photos and put them in any what way. But something to remember for these particular pictures is that we have taken them an equal time apart. So it could be 2 seconds, 1 second, half a second. Your friend's car is really struggling. This is every 10 seconds. Whatever the time is between every single photo is the same amount of time. So I'm going to just say 2 seconds because why not? So every single time happens to be the exact same value. So what we can do is we want to show how the car moves over time in the same image. So we can use whatever program of our choice. You can use Paint, Photoshop, GIMP, any editing thing you want to use to combine them all together. So now we have all the cars in the same image. And from our understanding, we still know that the car was moving to the right. So we know this is our first position and we've gone to our second, third, and fourth positions. And again, because we took these pictures, we know that the same amount of time passes between every single one of these images, which we said was 2. So we now see the progression of the car. We see the trajectory of the car in this image. And every single picture, again, is separated by the same amount of time. And the reason I keep repeating this is it's really important for motion diagrams that we have our images separated by the same amount of time, because we're going to be doing some math with these a little bit later, and we need to accurately know relationship between our different positions. And by having the same amount of time, we're going to be able to do calculations more accurately. So, right, again, we have some relationship between how our car moves related to time. Now, in this image as it is right now, there's no indication of if it's moving to the right or to the left. Our original images, we could put them in reverse order and our car is backing up instead. So we need some sort of way to show the direction of our motion in the motion diagram. Well, first, I don't know about you, but my drawing skills aren't exactly great. So we're going to need a different model in which we're going to go through and look at. But before we do that, I want to stop and do one of the stop to think questions that's in the textbook. So normally I'm not going to be doing stop to think questions in lectures. I just want to show you what these are in the textbook. So these are quick questions that I heavily recommend that you do. I have used them on quizzes and exams in the past. These quick questions just help you make sure you understand the section that just was before this. So in this case, I want you to pause the video and go through and try to solve this particular question. Okay, so I'm now assuming that you have paused the video, gone through, and answered car A or car B. So with this particular series of images, right, we have a car. It doesn't tell us which direction the car is moving, but it tells us there's an equal interval of time between the frames of both videos. So that would mean, let's say, for the sake of time, it is 1 second between each of our pictures. So it appears, for car B, by the time 2 seconds has passed, it has moved out of frame, whereas car A is still in frame for another second. So because of that, car B is going to be the car that is going faster, right? It's the same amount of time, however, it's moved out of our frame, so the distance it's moved has been a larger value. So this is not a motion diagram. This is a series of, this has it defined as frames in a video or pictures composited to each other. This is not a motion diagram. So we need to go, again, we don't know if the cars are moving towards each other, away from each other, are these totally different situations. So we want some sort of way to start more accurately describing how these objects are moving. And for that, we need to look at a model. So a model is something that can save us a lot of time, as we can really simplify down our problem. So for example, let's take this car and we want to transform it into some easy to draw shape. Now, I know there are varying levels of art skills in this class. I'm going to tell you 100% if I have to draw a car, it looks something like this every single time. and that takes a lot of time. I don't want to have to keep drawing this every single time I need to draw a car. I'll draw it if I only need to draw it once, but if I'm drawing the same shape over and over, drawing a point is a whole lot easier. So I could take this car, and I could take the center of the car, and I could just draw a point. So now my car's a bunch of points. Maybe if you don't want to use points, that's fine. Maybe you want to use squares, you could use a square. Maybe you really like triangles, you could use a triangle, whichever shape that's easier for you to draw. The textbook is going to use points for its motion diagrams because it's the simplest of the shapes. But basically we're transforming our car and we're converting it into a nice, easy to draw shape because we want to use what is referred to as the particle model. And in reality, for a motion diagram, especially in this class, we don't care about the shape. I don't care if I have a semi-truck versus a car. Because of the approximations we're going to be making in this class, I could treat them both like a baseball, and it's going to be the same exact math. So I can just use a point to explain what my vehicle looks like. So throughout the textbook, there are going to be a couple of different models and modeling techniques that the textbook uses. Primarily, we are going to be focusing on using the points or using some sort of box. Box is a little bit more later in the semester when we're dealing with energy. Points pretty much every other time that we're looking at motion. So here's an example of, a model, in this case, the motion of a rocket launch. So it starts on the ground and then it starts moving upwards to get out of Earth's orbit. Now, if we look at this as it is, it's not very descriptive. Here we have numbers to indicate which direction the points are moving. So that's really beneficial because now I know in this case that my rocket is moving upwards. But there's a lot of other information I can include on a motion diagram. So this is what is going to be kind of referred to as an incomplete motion diagram. There is stuff missing in this motion diagram that is going to help us accurately describe the motion, in this case, of our rocket. So make sure to watch the next two videos to figure out how to go from a bunch of points to a complete motion diagram.